Hi guys, thank you for coming to OLED Wave paper reading channel. Today we're gonna be reading a classical paper for generative AI. Its title is Variational Autoencoder, and although this was published 10 years ago, but this is the foundation of the popular vision or video generative AI technique, for example, Sora. And today we're going to be covering its key ideas and its usage in deep learning. First, we start off its key idea ELBO, and we also will illustrate what the reparameterization trick is. We also will explain how do you apply the concept of encoder and decoder in deep learning together with VAE. First, how the problem is formulated. Suppose you have a latent variable z, latent random variable z, and you want to go from z to x, and x is you can either call the real world sample or observed sample. Okay, we usually call it observed sample. In the video or image, it's the image or video. So the question is, how do I get this? And I wanted this probability to be as high as possible, right? So I can get more accurate real world video or image reconstruction results. Okay. And the goal, and we can set a parameter for this. Let's call that theta. And the goal is to have this to be as close to the P of X, the real world samples distribution as possible. And you can see this is indeed called the generation. Of course, everything, if you want to generate something, you have to estimate something, right? Or in this autoencoder, you do have to have an estimation stage, which is supposed, because originally in the training data or the a bunch of data set, a bunch of data in the data set, you have lots of observed sample of X. And the question is that how do you go from the sample X to Z? And you want this to be as close to the distribution of the PZ as possible. That makes sense? This is the estimation. So if I write this thing in a deep learning network model or the encoder and decoder, it will be like this. This is the encoder. This is X input. And this will be the output of Z. And Z would be output to decoder. Decoder's output is the generated X, and the parameter that controls the generation is theta, and the parameter controls the estimation is called phi. Okay, and then let's now take a look at the ELBO's definition, because it's a lower bound. You know, it's in mathematics, people always want to maximize the lower bound. And let's see how the ELBO is being defined. ELBO, given the two parameters, two sets of parameters, theta and phi, is equivalent to the expectation of Q phi z of x given x. This is log e of x and z minus log Q of dx given x, right? That's the definition of it. But just to see better what it does, let's write this equation in the first decompose the equation. Okay, let's first define this just as y. Okay, for simplicity, and then you will have log p x to be theta. We got the theta here. Theta log this, right? And then you have q phi the given x. That you can see for the first part, it's easy to see. This is just this is what eq phi log p theta of x plus let me write this in a red version here. But this thing, if you, because this is integral over integrated over q phi, so it has nothing to do with p theta. So you can write this in here. Actually, you can even throw away the p theta here. But we leave it here because this is generation. We need the theta here, and then this is what? This is the Kerr divergence of q phi and the p theta. Am I right? Because this is always negative, the second term, or this term is always non-negative, and this thing is always smaller or equal than this. And this is called what? This is called evidence. Because you always have the real world scenarios x to compare with this. You want to maximize this, and this is how you want to maximize the evidence. But maximizing this is very, very difficult because it involves, say you have this latent variable. Let me write a few more equations than this. And this one would be equal to the integral of p theta x given z times pz. Am I right? So it integral over all the distribution of z, and getting all the z's are difficult. So this is always very, very difficult to compute. So instead of trying to maximize the evidence, people thought that, okay, I can try to maximize ELBO over here. So the concept was, if my ELBO is here, because this is a lower bound, my evidence should be here, right? This is my lower bound evidence. But if I can capable of pushing my ELBO to here, this is my new ELBO, and then I would, this evidence would be no longer here, then it would be somewhere here, right? That means by maximizing your lower bound, your objective function got actually pushed up. Make sense? So that's the definition of ELBO. But how this thing is being actually computed in the actual VAE is actually done in a second approach, second way. So you can see, let me write down this log p theta z plus log p theta x given z q phi p of x. I'm sorry, it should be this one. Make sense? And then I write this thing into two parts. We'll move this, write this thing first. Okay. This is EQ phi. What is this? Write this. How about this? This is fair, right? Let's see what the second term is. The second term is actually the KL divergence, right? This is done on the Q phi. And the first term is what? Let me write the actual equation of this, okay? Make you feel, make you understand it better. Okay. Then you can see this is better. We don't use any, back propagation algorithm, because you can see that this is KL divergence. Suppose P theta z, actually you can just remove the theta here, because this has nothing to do with theta. Z should be a hidden variable. How do you see that? And then this thing you can see, leave it on is fine. So you can see, suppose P of z follows a normal distribution, and this one follows also, I try to make it, or I force the Q phi z given x to be another normalized distribution, right? They have a mean, they have another mean, they have another standard deviation, and there's a standard equation for computing these two KR divergence, right? Then the problem is that how do you define this mu and theta? Or how do you generate these things? Because z does not have a mu and theta. This is the first or the second reason why we need this reparameterization trick. But the most important trick is this. Because when you want to maximize the ELBO, so you definitely need to take the derivative of the ELBO, am I right? Let me just write the second term. Let me call this the first term, term A, and the term B. And just write the term B, okay? So applying the chain rule, you will get this. And then you would have this. This part is very difficult. Let me first check the second part, okay? The second part is fairly simple, because if you look at the decoder, okay, you go from z and you estimate your x, and then you see what this is. This is the gradient the gradients in this decoder. Am I right? You can use just autograd or back propagation to compute this by looking at the samples that pass through the neural network samples, pass through the neural networks. And by doing this, this is simple, right? You can just do the Monte Carlo sampling. Then the second term will become what? You get it? Are you with me? P theta xi z. Make sense? Or probably z you have to sample the ISD, right? This is simple, but for this part it's difficult. First of all, you say, okay, wait, I know how to do this because this is encoder, right? I can get the same thing like you mentioned here. I can also do back propagation, but the problem comes, then you cannot use Monte Carlo sampling because there's no distribution over here. This is a log distribution. This is a derivative of distribution, right? And the only thing you might be able, you can try is that suppose the Q phi is differentiable, but no, of course it's differentiable. If it's see that has a closed form solution, then you can just keep doing the integral. But then you cannot leverage the powerfulness of the. Then it's very, very difficult because most of the time the Q phi won't be having a closed form solution of its derivative, right? Let me write it down. Usually, no closed form solution for this. No. Then the question is, what do you do? So here comes the reparameterization trick. So look at Z. Like we mentioned, Z follows the distribution of right? So you can write the Z as mu of x plus epsilon sigma x. And epsilon follows a distribution, p epsilon. Okay. I don't think this is right. This might not be right. Anyway, you just use this. By decompose, because you know how the Z distribution is, you can convert the random variable Z into the following three random variables, and this particular random variable follows the normal distribution, or most time the follow is normal distribution. Okay, but we won't be using that right now. Then you see this equation, this part B, it will become what? Use yellow. It will become, it used to be the Q phi, right? So now it'll be Q, sorry, because it says, as I write a P epsilon. And you can see the Z and the X are gone, just a P epsilon. And then you will have log P theta theta u plus ux plus, anyways, epsilon theta x, and then also this one. Q phi ux plus epsilon theta x given z. Am I right? So now the question is that because well, if you do this, let me write another one more step. Let me write it here. Okay, this integral of p epsilon times log. Do I have the okay? I forgot one thing because this suppose you wanna have, because it goes from the yellow one, right? I forgot to put the gradient nabla sign here, right? And then you got this. But when doing this, okay, I think I write an extra thing here. I shouldn't have this. This one. This is the equation. And then I would say if you do this, then I can get this time you just do the derivative on the theta, right? It's not phi, it doesn't matter. Then you can keep writing this. You can do the multicolor sampling now, right? Because there's no derivative on the, you can just move the derivative inside. Make sense? Then you can do the multicolor sampling now. And then it becomes what? It becomes okay. Because the ux and the epsilon x are actually, let me write this here. They are the have the parameter of theta here, right? Because it's a generation, right? It's all about the x here. Okay. Then these two things can be, these two terms can always have a derivative because you pass these things through a neural network, right? Because this is a generation. Are you with me? This is yes. This term is I think this term is encoding, right? Encode. This is part is the decode. For decode part, you got x and z. I forgot this should be x given z, right? X given z, given this. So you can see that by controlling the, I think I'm wrong here, sorry. This is X. Okay, makes sense. But this part, you can just write this, because usually in Monte Carlo sampling, then you get this. Then this part is log P of theta XL, and the UX plus epsilon L theta X. I don't think the D is over here, it's gone. So you can see by doing this, you can keep sampling not from Z. You no longer sampling, you start from Z. You start from epsilon. For each L, each sample, you just sample one, you get X, and you compute the derivative. How do you get the derivative? Because this thing is the decoder, right? It's a generation. You have a neural network generation neural network. You can get the back propagation, you can get autograd. So this part is the gradient. It's easy to get. You get from PyTorch, TensorFlow, and then this you summate over this. Then it solved the B part of the ELBO's derivative, okay, or the gradient. And the first gradient, like I said, by doing the reparameterization, you solve the how to solve the part B. But it also helps you to solve A, because in this R trick, you define the mu and the sigma. So then the mu and the sigma can be plugged into here, right? So the Z is mu and the sigma is what? 0 and 1, right? Let me write another pen. So the standard Z, or standard, what it should be is 0 and 1. Then you have your own mu and the sigma. Then you want this to be as close to this as possible by minimizing the KL divergence. That makes sense? All right. I hope you are with me. I think I solved how to maximize the ELBO, and I explained how do you compute the derivative of the ELBO, both part A and B. Then what's next? The next part is that we have to look at this, because we changed the mu and the sigma, so we have to do a little bit change to here. Let me draw it. Yeah, maybe somewhere here. Let me draw a new one. Now you have X still pass through the decoder, but sorry, encoder. An encoder controlled by phi, like I mentioned, but this time it will generate lots of samples, so you can get the mean of the X and the standard deviation of X. And the two things will be used to form Z. I missed the one thing. If you can pause the video and see what's missing. Right. you have to have a epsilon, because z equals to mu x plus epsilon times sigma x. So this is a trick, or the R trick, reparameterization trick. It's very important in the VAE, and after this, you pass that through a what? Decoder. Decoder is controlled by the parameter theta, and you get what? The reconstructed or x, okay? And what do? Then you have a module for comparing the difference of the x with this x. You can either use the maximum likelihood or MSE. It's up to you. And also for this theta and mu, remember you want to compare that with a standard normalized distribution. So you put this into a KL divergence computational stage. So you have two losses. The first is MSE loss, or what do you call that? Cross entropy based loss. And the second, you have a KL divergence loss. And what do? Of course, you add these loss together, so you have a overall loss. This is called ELBO loss. And then you do the back propagation. You can see everything got updated. Make sense? All right. I think, and in the end, I think the goal was to see whether you can get. The goal is to get the P of x given z under the parameter theta to be as close to P of x as possible, because this is a real world sample and this is a generated, and you want to generate to be as close to the real world probability distribution as possible. And what is interesting is that this is a posterior, and this is just overall distribution, a marginalized distribution. And you can see how we can control the factor of z and theta to make everything to be as real as possible. Okay, I think that's my illustration of VAE, Variational Autoencoder, and I emphasize the importance of the reparameterization trick, and I explain the evidence lower bound, and I also explain how these whole things are being used in the deep learning framework. All right, thank you so much. If you like our channel, please hit subscribe. And if you enjoy watching the video, please share that with your friend, and stay tuned.